welcome back. In this lecture, I will be discussing Scatchard-Hindenburg theory, which is basically a theory which avoids usage of the van der Waals equation and taking out the key issues with the van Laar theory. Okay. If you recall, van Laar assumed the following, okay, for the theory. Okay. Now, Hindenburg defined such kind of systems as a regular solution. Okay. So, regular solution assumption would be where you can consider Sx and Vx to be 0. Okay. So, what did Scatchard-Hindenburg did basically, or what basic contribution of Scatchard-Hindenburg is basically to modify the van der Waals to remove the dependency of a van der Waals equational state. So, the theory is nothing but essentially a modification of van Laar theory to remove dependency on van der Waals equation of state. Okay. So, in order to do that, what Scatchard-Hindenburg did is they defined cohesive energy density. Okay. So, they defined term C, which is cohesive energy density. C is equal to delta U vapor by VL. So, this is the formalism of the cohesive energy density, where this is a molar volume, and delta U vapor or VIP is nothing but the difference in the ideal gas at T minus the energy or internal energy of the liquid at Tp. Okay. So, this is the difference where. So, essentially the internal energy of the liquid with reference to the internal energy of the ideal gas at that temperature, that is a cohesive energy. Okay. And now, in order to come up with the mixing model, where the major problem with the van der Waals equation of state was, so they in this theory the model for cohesive energy density of mixture is considered as C11 V1L x1 square plus 2 C12 V1L V2L. This is like molar volume of the liquid x1 x2 plus C22 V2L x2 square x1 V1L plus x2 V2L, and C12 is basically C11 and C22. Okay, and this particular term is nothing but your cohesive energy density of mixture, which is defined in the following. So, this is like liquid minus U ideal gas mixture minus this is nothing but also would be your delta U mix, okay, of this vapor. Okay. So, this is the model considered by the Scatchard-Hindenburg theory. Now, this can be further simplified by considering the following, that Now, one of the important thing in this case is we have considered Vx to be 0 and Sx is of course a 0, remember that. Now, in order to simplify, we define term called volume fraction of component I is going to be xi Vi divided by x1 V1 plus x2 V2. Now, with this your delta U mix is x1 V1 plus x2 V2 C11 phi 1 square plus 2 C12 phi 1 phi 2 plus C22 phi 2 square. Okay. So, this is the expression, we have it. Now, since Vx and Sx is equal to 0, this also means that Ge is nothing but Ue, okay, and delta U mix, okay, is Uxs is nothing but U mix for total minus x1 U1 minus x2 U2. So, this is something which we can also make use of the difference with respect to ideal gas, knowing that delta U mix is nothing but Uxs for ideal, this is going to be 0. So, if you do that, Ge is Ue and this is something which for ideal gas, okay, this is the vapor minus x1 delta U vapor 1 minus x2 delta U vapor 2. Okay. Now, this may look very complicated, but it is actually straightforward if you put down all this understanding of this individual variable. Now, I am going to write this now Ue, because this is available, and this also we can directly write the for example, this one would be your C11 VL, okay, this is by definition, and this will be your C22 VL, and this of course we know from earlier. So, this further can be simplified. Phi 1, phi 2, x1 V1 plus x2 V2, okay, right. And now, what I can do is I also can write this as x1 V1 plus x2 V2 and this phi 1 phi 2, and this can be written as delta 1 minus delta 2 square. And what is delta here? This is the solubility parameter. So, delta 1 is nothing but C11, okay, is a square root of the cohesive energy density, is a solubility parameter, okay, and similarly delta 2 is C22. Again the solubility parameter. Okay. Now, this if you put it here, you should be considering that C12 is nothing but C11 C1 C22. Okay. So, that way you can, these two expressions are synonymous. Okay. Now, this solubility parameter is something which you can extract from the experiment, and that is why this becomes a very, very useful theory in order to connect the experiments. So, we may be doing some example in the later stage. Okay, now, given that you have an expression of Ue in terms of this, and this is nothing but G of E, okay, where again remember that this is the mole fraction, molar volume multiplied by x2, volume fraction of component 1, volume fraction of component 2 multiplied by the difference in the solubility square of that. Okay, and this is nothing but g of e. Now you can connect this thing to your activity coefficient, so which I am not going to derive, I will just write it here. And this is a very famous expression, which is basically regular solution equation given by Scharchard and Hindenburg. Okay. Now, so you can rearrange these expressions. So please understand that basic assumption in the Van Laer equation and as well as the Scharchard Hindenburg is that your SC and VE excess entropy and basically the volume is 0. So that means they are considering regular solution. The difference in the Van Laer is it uses the Van der Waals equation to get the mixing parameter, whereas here it relies on the cohesive energy density. So in other words, the expression here I should be able to also connect to the Van Laer form. So let me just try to do that. If I do make use of the Van Laer form, then the A dash is going to be V1 by RT and B dash is going to be V2 by RT. So here again you can clearly see all these are positive, indicates that log of gamma 1 is greater than or equal to 0 or gamma I is basically greater than 1, which means basically it is a positive deviation from the Raoult's law. Okay. Now the other important thing is that the solubility is basically a function of temperature, but if you multiply with V by phi square, then this is more or less constant, okay, and it becomes independent of temperature. This is based on the experimental observations. Okay. So with this I will stop here, okay, and in the next lecture I will start polymer solution followed by set of examples which would illustrate the concept which is shown here, and that would be the end of this course. Okay. So I will see you in the next lecture.